Welcome to week 3. And this week we're going to cover some time series, get involved with some time series data sets, and run through some meteorological data that we collect here in Delaware, and plot some air temperatures and some dew points, and then we go through to an assignment where we try and plot wind gust and wind speed. So before we get started and run through all of this week's tutorial, it's called Time Series Fun with Dios, let's real quick just go back over this in-class exercise from last week. So same thing, just like we did in the tutorial, we got to load in our libraries. In this case, NetCDF4 and fields. Open the file. We want to grab, now instead of this time, we want to grab DQF instead of ST. So we load in this file. If we want to make sure like how it's exactly spelled, where it's capitalized, whatnot, we go NC file, and we can see that just by printing it out, we see that there's 4 variables. This is the data type. It's a float, which is just a floating point number, and then this is the variable name. So band 15, DQF, SST, and projection. And so we want DQF, so we just need to load in via NC_var_get. So NC_var_get, we need to provide 2 arguments. The first is what NetCDF file do you want to open a variable from. In our case, it's called NC file. And then which is the variable name. And in this case, it's DQF. This is the variable name. And so I should go into this a little bit more detail, and just so everybody is aware of what I'm talking about. If we do a help on NC_var_get, we see that there's a couple arguments. One is NC, what the object class NetCDF4, it's just the file, it's just what file to read from, and then the var ID, the variable ID, and so what variable to read the data from. So in this case, we want to have NC equals NC file, and then the var ID equals DQF. And then, boom, there's DQF. And again, it's not vectorized yet. We'll need to do that if we want to actually understand a summary of the data, but it's not necessary to manipulate that data set exactly. So we also want to load in latitude and longitude. And notice the same thing can be put in here. We can actually declare these arguments in an official way instead of the shorthand way. What I mean by that is where we're actually saying, okay, the NC argument is going to equal NC file, which NC file is this NetCDF file that we opened up here. And then the var ID, the variable name, is latitude. So we do not need to explicitly declare the arguments here. We can just do something like this, where we have NC file and then longitude. However, if we don't do a specific declaration of NC equals and var ID equals, then the arguments must be in the same position as they are designed to be. So in this case, we have NC and then a var ID. And for example, if we would switch this around and say longitude, and then from NC file, it wouldn't run correctly because the first argument is not of class NCDF4. So if we run a class on NC file, it's a NetCDF4 class. So now we know, okay, NC is going to be equal to NC file, and then the var ID is longitude. So this is the shorthand way. So now we read in lon correctly. So once again, we just need an x on our plot, which is going to be longitude. The y-axis is going to be latitudes, and then the fill, or the z, is going to be DQF. And DQF is, remember, a data quality flag. So we're going to go ahead and, looks like I forgot to run lat. We don't have lat up here. We did not declare. I did not run that line. So let me go ahead and run that, and now we can rerun, and again, this takes a couple seconds. And once again, there are faster methods for plotting with all of this. There are faster ways to actually go about doing this, but for now, we'll just use image.plot because it's a pretty intuitive way. It's a good one to learn first. So now we see we finished running down here. We're back at our sideways caret and cursor, and we're just going to wait for the plot to pop up over here for right now. So any second now, this should pop over. And again, this is also one of those weird things where sometimes R has to get warmed up a little bit before it really starts firing on all cylinders. And, again, we're in a 5.5 million point matrix, so this is a pretty large data set, pretty big. But here we go. Here's the plot we wanted, DQF, and once again, where we have 0 values, those are good data. Where we have this orangish yellow, there's clouds, and then this is land. So moving on, getting back into the time series. We're going to cover some time series data from DEOS, and for those of you who don't know, DEOS is the Delaware Environmental Monitoring System. Delaware Environmental Observing System, and CEMA is the Center for Environmental Monitoring and Analysis. So but CEMA is the overarching organization that is in charge of DEOS, and both of these things work together to create a dense network of weather stations across Delaware. And for those of you who haven't seen it, we can go to deos.udel.edu, and we have real-time weather information for a variety of stations. And once again, this is the highest concentration of professional weather networks in the entire United States. So you can run through whatever you want, and you can look at rain totals, and we even have some radar and things like that as well. So anyway, we're going to be using this kind of data we're going to be using time series data from one of these stations. Before we get into that actual data, there is an essential skill that I wanted to cover. That skill is the for loop. So these are very key. This is a very key skill in R. So real quick, I'm going to head over here, create a new R script, copy that over. And the first thing I'm going to do for this example is I'm going to create a numbers list. And numbers list is just going to be a sequence of numbers from 1 to 10 numbered by 1. So we have 1, 2, 3, all the way to 10. And what I'm going to do is, this is my for loop, and what I want to do is I want to multiply each number in this list by 8 and then print the result. So here's my for loop. For, which is a special character string in R, hence why it's colored a little bit differently than some of these others. For, and then a condition. So the condition here that we want to have is for I in numbers list. So I is going to be the ambiguous loop identity, and we're looping through the numbers list. What we want to do here is we want to multiply I by 8, and that is temporarily going to be stored as temp number. So temp number is going to get overwritten time and time and time again. Each time it gets overwritten, or each iteration of this loop, we're going to print the number. And everything that we're doing inside of this for loop is inside of these curly brackets right here. So again, for condition, so condition is in these parentheses, do this, which is in the curly brackets. So when we actually go ahead and we run this entire for loop, you see we have our numbers list 1 through 10, and then multiplied by 8. So now if we just take a look at what I is 10 because we went from first to last of numbers list, so we got to 10, and we look at temp number is 80 because we had 10 times 8. So if we could write another for loop here, and we could just say for I in numbers list, print I. So 1 through 10, because we ran through each different value within numbers list. So this is your for loop. So we can also have nested for loops in here. And what I mean by nested is we can have a loop within a loop. So let's say this time we have a numbers list and a letters list. So numbers list is 1, 2, 3. 1, 2, 3, and letters list is A, B, C. So A, B, and C. So I want to do, say, for num in numbers list. So here's my for loop, and I'm starting a for loop, and then I have a condition, num in numbers list. Do this, and now we have another for loop. For let in letters list, print num, comma, let, and so we concatenate this together. So if I actually go ahead and run this, see we have for num, we have the number is 1, and then for each time we have a new num, we want to print all the letters in the letters list. We have 1, 1, 1, A, B, C, 2, and then A, 2, and then B, 2, and then C, 3, and then A, 3, and then B, 3, and then C. And so if we were to switch this around, let's say for let in letters list, for num in numbers list, what I would get here is I would get A, B, 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 C, 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 1, 2, 3, and let me just go ahead and run that and actually do that, and boom. So we have A, and then we go through all of the numbers, B, 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 all the letters. So that's kind of how this is structured, and just pay attention here that when I have my cursor to the right of one of these curly brackets or regular parenthesis, I can see the beginning and the end. So this is at the end of my nested for loop. It's called a nested because this for loop is within the larger for loop. So here's my last curly bracket, and that corresponds to the first curly bracket up here. So there's another thing that we can have here, which is a more complex example. And this is a multi-conditional statement with an else. And so what we're going to do for this example, which is a little bit more complicated, so we still have our same numbers list and our same letters list. And we're going to say for num in numbers list, then for the letter or let in letters list, if the number is equal to 3, remember the double equals means is absolutely equal to, and let is equal to B, I want to print out the number in the letter. Otherwise, or else, print not what we want. So notice the number of open and closed curly brackets here. So we have an if-else nested within a for loop, nested within a for loop. So let's see what happens here. Not what we want, not what we want, not what we want, and then finally, boom, 3 and B. And so what happened there was if we finally had the scenario where the num was equal to 3, the letter is equal to B, and then we were able to print out, yeah, this is exactly what we wanted to print. Otherwise, not what we want. So that gives you a little bit of an example. Now let's apply this with an in-class exercise where we are going to debug this for loop. And so again, for those of you who might need a little refresher, debug means fix. So there's some problems with this. We have curly brackets out of place. We have some missing things or some incorrectly used for loop instances, and if statements. So go ahead and try to fix this. We are looking for this output right here. So once you try and fix it and go about it, try and get this output to try and match this output right here. So now we're gonna get rid of all this, and please work through that for loop. But for right now, we're going to run through DOS data. So the data set that we're going to be using is called dios.csv. And so this is our first CSV file that we're going to be playing with here. So I'm going to copy that over, and we read a CSV file in with the read.csv function. And this is a base function. We don't need to load any packages to use this particular function, but it works the same way as NCOpen does. So it's just like before, we had to specify a path and then the file name. We also have to do that here for read.csv, and there's a couple other extra arguments here within this function. So just so I pull this function up, I'm going to run question mark, or remember question mark is also help for read.csv. And here we go. Read.csv, it takes a file, it takes a header. Is there a header? How many lines to skip? And then strings as factors. And so we come right down here. The reason I have strings as factors equal false is should character vectors be converted to factors? And no, the answer is that we do not want character vectors converted to factors here. So let's go ahead, and for me, my path is users, James, documents, GitHub, geog 473, 673, and then datasets. Yours might be something like downloads, datasets, and then DOCSV. But remember, if you're ever confused, go back to square one, put in your quotation marks, hit tab, and then this is where ours thinks you are right now. So I need to go to documents. For me, I need to go to GitHub, geog, and I'm hitting tab in between each selection here. I got to go to datasets, and then I want dios.csv. Run that file. And boom. So I'm going to run ahead on Dios data, and this is what it's looking like. We have a timestamp variable, an air temperature variable, dew point, wind speed, wind direction, barometric pressure, solar radiation, wind gust, and gauge precipitation. Let's go ahead and run a summary on this data and see what we're working with here. So we see automatically we have some pretty crazy air temperature data. We have a minimum of -51 and a dew point of -53. Probably some bad data. We don't typically see that too often in Newark, Delaware. And we also see some wind speeds that make sense. You can't have a negative wind speed. And so that looks pretty good. And we have gauge precipitation, which also makes sense because we can't have any precipitation values below 0. Can't have negative precip. So I want to run call names on this data just to find out the variable names. Some of these variable names look a little funky, so let's find out the variable names. Run call names here, and we see that they're a little wonky. Some of the file names, they have their units, and as kind of an extension, air.temperature.degrees.celsius. So we want to rename that. So what we're going to do here is we're going to use the names function. We're going to rename these ugly variable names. And so we're going to run a names on Dios data. And names brings up the same exact thing as column names here for this type of data set. And we want to rename them, all of these. So if you do this, run a length on Dios, length on the names of Dios data, the length is 9. Now if we want our length on this, it's also 9. So these have to match up, and in this case it has to match up with what we're replacing. So these can't be out of order. We can't have air temperature. Air temperature must be the second thing that we're naming because of that position in its list, and sure enough, there's air temperature right there. So we could not put air temperature at the end. This is a gauge precipitation variable, not air temperature. We're going to go ahead and run that, and now we're going to rerun names on Dios data, and much nicer. We have date time, air temperature, dew point, wind speed, wind direction, so on and so forth. Let's go ahead and index. And let's see what let's print out the first date time. And remember, if we want to call the first date time, all we have to do is we need to call our data set. The $ is the variable query character, and we do in fact want to print out the date time, and then we want the first one. We're going to run that, and the first is April 4th at 4:05 in the year 2014. Now we just want to run a class on this Dios data datetime. And we see the class is a character. And this will prevent some issues because it's a date. It should be a date class. So here's what we're going to do. We're going to convert this to a datetime class. Convert. And this is how we're going to do it. There's a few different functions that you can use with date. In this scenario, what we're going to do is we are going to use as.posixct. Let's run a help on that. So this is a datetime conversion function. And POSIXCT is a universal acronym for dates. And do not ask me what this acronym stands for, but you use this function to convert an object between two classes. And so what we want to do is we're going to want to convert this from this character class to a datetime. So the way we're going to do that is this function, and we see that this function takes an x, the R object to be converted. So in this case, our x is equal to the Dios data datetime variable. And just so you have an idea what that looks like, it's just this vector of these date strings that are in characters. Then we need a format. And the format is the structure. Is this year, month, day, month, year? Are there hours and minutes? And so on and so forth. And the way that you declare a format is like so. So this might look a little weird at first, but what we're doing here is we're using the % right here, followed by the date identifier. In this case, our date identifier is, if I go back up here, I print it out, we see that we are year, 4-digit year, dash 2-digit month, dash 2-digit day, space, 2-digit hour, colon, 2-digit minute. So the format here, capital Y, is the date identifier for 4-digit year, dash, % lowercase m is 2-digit month, dash, % lowercase d is 2-digit day, space, % capital H, 2-digit hour, colon, % capital M is 2-digit minute. This might be confusing. I still have to look this up from time to time just to double check things, but this is how we declare our format. And so this way, when we run this, unless before we resave it, let's run it, and boom, now we actually have, it's automatically assuming that we are in Eastern Daylight Time. It added in a seconds as well, and now notice, but other than that, there's not much difference. So let me fully run this line now. So we are just overwriting what was in date time with this. So now, if I run a class on Dios data datetime, it's a POSIXCT or POSIXT class, which is just universal time identification. So now that it's in a datetime class, it makes things easier. It makes things easier for plotting. So what we're actually going to do now that we have everything that we have the dates correctly organized, is we want to subset our data set. And in this case, we want to subset it using a lower indice and an upper indice. And so this is going to be kind of tricky. So what we want to do is we want to say, which is the minimum value where Dios datetime is less than 2014-04-04 at 000. So we run that line, and so what low end is that is the first variable. So this is an index identifier. So if we were to change this and say, let's do June 4th and run that, that would be 17,520. So that's the index of June 4th. So Witchman is a great function to find out the index there. And what we're trying to do is we're trying to find where the date time value, the closest value to where the date time is less than this date string. Let's go back to the 4th. That is our lowest indices. So if I run this, low end, it's just 1. If we have upper end, and so what I want to do now, so we just want to subset just this one day, or sorry, this is 1 year. We have 0404, 2359. See that the value is a 105,360. So, and this makes sense. We have 182,000 points in here, and this is 5-minute data. And just as a summary here, our max is 2016, and our min is April 4th, 2014. So when we try and grab just a year here, we don't need the entire data set. That is why we're trying to subset this. Now that we have our indices, and so upper end, oh, I didn't run this. Go ahead and run that. Our indice again is 105,360. And so once again, that's going to be the closest value to 2015-0404 at 2359. Now that we have these indices, we can use these to subset or slice the variables that we want. And so what we want to do is we want to apply air temperature. And we want to do this from the low indice to the upper indice. So if we subset like so, we see that our indices select April 4th, 04 all the way down to April 4th, 2015. And we want to do the same thing for the air temperatures. This is 1 year from April 4th, 2014 to April 4th, 2015. And then I have a type, which is line. Color equals red. X label is going to use the paste 0 function, which we will cover in more depth next week. And that paste 0 function is going to identify the low indice to the upper indice, but for the daytime values, it's going to say 2014-0404 to 2015-0404, and then the Y label. And then we want to add a title to that as well. So let's go ahead and plot this up, and boom. May, July, September, November, January, March. And so this is our label identifier, 2014-0404 to 2015-0405. Celsius on the left. And it looks a little bit different because we're so used to seeing yearly time series from January 1 to January 1, but in this case we have April 4th to April 4th. So we have a kind of a nice sinusoidal curve here, just like we would expect lower temperatures in the winter months. So that's the tough way to subset. Well, not necessarily the tough way, but not the easiest way to subset. So if we wanted to, instead of doing this the old-fashioned way where we have a low indice and an upper indice and we subset this, we can use the subset function and declare our 2 date times that we want and then make an entire new data frame. So I'm going to go down here, copy that over, and so here's our subdios, and this is what we're going to name this variable where we have a subset of the dios data. And so I'm going to run a help on the subset function real quick, and we have an object to be subsetted, so dios data is x is equal to dios data, and we have this subset, which is going to be the dios date time between July 4th, 2014 and July 11th, 2014. So we're just sub-selecting 1 week of data. And remember, you want to rename this as something new because you don't want to overwrite our original dios data. Run that and run a summary on subdios. And we see that, yep, our minimum year or our minimum daytime is July 4th, 2014, and our max is July 11th. Now that we have that already subsetted, we do not need to use the indices that we have pre-recorded. We can just use the variables. So we want to plot, we want our x or our x dimension to be daytime, our y to be air temperature. We want a line type, color to be red, and we also want the x label to be the same. And we also have this additional y limit down here. We want to split between 5 and 40. So if I run that plot, it's cool. This is a week of temperature in July, and you see that diurnal shape, the diurnal difference. And let's say I just want to add dew point to this. If I want to add something to this plot and I want it to be a line graph, we can just call this lines function. And we can call dew point and we can make that color yellow. So let's go ahead and run that line. And we see that it added the dew point in here. So we notice that over here, the dew point is just about equal to the temperature, so we can kind of assume that there was some precipitation on that day. And then we want to add a legend to the bottom right, and then a title. So all of this is happening because we have not queried a new plot window, so we can keep adding things to this. So that is how you would subset a data set and a time series data set especially, and then plot it up. So that concludes the tutorial. For the assignment, what I'd like you to do is subset the data set to January 2015, convert wind speed and wind gusts from meters per second to miles per hour, plot the wind speed and wind gusts on the same plot. What you want to do is plot wind gust as points first, because otherwise this will drown out the wind speed. Then plot wind speed as a line second, and you can do that using changing the type from L to P. Add the legend. Compute the correlation coefficient between wind gust and wind speed using core, the core function. So you might need to run a help on that, help on core, to understand what needs to go into that. Add to the title of the plot, and then just submit the resulting plot to Canvas assignment week 3. So this is what it should look like. You have wind speed. For me, you don't have to plot it the same colors, but I've plotted it with wind speed as dark blue and then light blue wind gusts. We see we have these higher up wind gusts and some very high wind gusts going on right here, over 40 miles an hour, which is gale force winds. And then we have our wind speeds down here.